Welcome to Unite Now, where we bring unity to you, wherever you are.
Thanks for tuning into this talk on ArtEngine and AI-assisted artistry. Since you're watching, you've most likely heard that Artomatix has joined the Unity family, and you're probably curious to learn a little bit more about who we are at Artomatix and what this means for Unity. The goal of this talk is to answer these questions and give you a wider context around where we see the industry going and how Unity plans to lead the charge. Before we get into that, though, I'd like to introduce myself. I'm Dr. Eric Risser, the founder of Artomatix, where I've also led the technology development for the past 8 years. The reason why I'm giving this talk is because Artomatix's history, especially in those early years, is largely entangled with my own. You see, before founding Artomatix, I was already working in AI artistry in academia. My research topic sat at the intersection between machine learning and computer graphics, where I focused on synthesizing new unique images, sounds, 3D shapes based on man-made examples. Over the years, I published a couple SIGGRAPH papers, and I put together some pretty nice prototypes on the topic. So then when I finished my doctorate, I noticed that this kind of technology didn't really exist in industry in any meaningful way. And I was a little worried that unless the people who were really pioneering the field in academia led that charge, it never really would. Also, I noticed there was a pretty big problem in industry, and I wasn't really sure how else it was ever going to be solved. You see, digital art has gone through an evolution over the last 20 years, but as the quality has gone up, so does the time it takes to make it. And it's not just the main characters we care about, it's all this other stuff in the background that takes forever. This has gotten so bad that Grand Theft Auto 5 took 5 years and cost $280 million to create. And the thing is, it's not even Grand Theft Auto 5 that's the problem, it's Grand Theft Autos 1 through 5 and the curve that forms. You see, it actually mirrors the median video game development costs almost perfectly over a 20-year span. Or if we were to put that another way, games are taking significantly longer to make. The reason is that art creation is still an almost entirely manual process. There are more artists now than ever, and art tools are getting way better and way more efficient, but relative to the explosion in demand, there's just no way for an inherently manual process to keep pace with the exponential increase in computer memory and power. That's where our mission at Artomatix over the past 8 years has kind of been. We want to build a new breed of artistic tools that introduces automation. We call this the example-based workflow. But what does that mean? Well, the idea is that you start from example data, which can be a scan you took, a quick texture you drew yourself, anything really. Then you add human intent. So this is what you want ultimately to have done. And then you add some kind of automation to that, or the computer does through some kind of advanced algorithm, say some kind of machine learning approach, or possibly something from data science. Basically, it executes on what you intended it to do. Then there's also an optional fourth feedback loop step, so you can keep iterating on your design. The goal of the example-based workflow is essentially to make every artist an art director, so you can create through curation. So this workflow is great for rapid prototyping, for mass production, or just getting an artist to the 80% mark super quickly so then they can spend their time focusing on the stuff that really matters to them. Now, the example-based workflow wasn't created by us. The industry is already familiar with this concept. We've just been calling it the photogrammetry workflow up until now. With photogrammetry, you take a bunch of pictures, so that's your example data. Then you add the human intent, which is, I would like a 3D model, and then the computer automates that process. So here's a picture of our first product, ArtEngine. It's a reimagining of that classic procedural tool, but based around machine learning. Thanks to this, it's able to automate a lot of the time-consuming and less creative work you do today. Now, I just said a big statement. Our technology is based on machine learning, and that makes it fundamentally different from the procedural tools you've seen before. I think it's worth taking a moment and explaining what this means. At a high level, you can think of procedural and ML artistry as the opposites of each other. In a procedural workflow, you write an algorithm, and that algorithm guides how the data is processed. On the other hand, in an ML artistry workflow, you provide the data, and that guides how the algorithm works. So if you were to think about this in terms of like an AI game character, so in a procedural workflow, it'd be kind of like if you were to program a whole bunch of if statements and equations that would tell that enemy player how you want it to behave in certain pre-predicted scenarios. Whereas an ML equivalent or alternative would be like starting with a blank slate, but giving it the rule that that dying is bad, and then you play against your ML enemy, and it, over time, learns from you and figures out how to get better and to die less. So let's start with a simple example by looking at ArtEngine seam removal feature. Given this input, ArtEngine reimagines what the seam region could look like, but tileable. I'd like to highlight how this is different from procedural seam removal techniques by walking through how one of those might work. So let's say we start with this input image, and first we would translate it by 50% along the X and Y axes, wrapping it around the borders as we go. So cool. Now we've got the original image on the left and the wrapped image on the right. You can then grab a plus sign shape patch out of the middle, and then you can blend that with the wrapped version. This trick can work pretty well for messy textures like this one, but you can notice a lot of ghosting around the lichen. There are ways to make this problem less noticeable. You can use graph cut tricks and things like that, but ultimately it's a limitation of the procedural concept, and you'll ultimately run into problems with more structured textures that have more distinct objects. The key difference between our approach and procedural is that procedural does the same process regardless of what the input texture looks like, which doesn't really make sense, does it? Like, if a human were doing seam removal, they wouldn't manually do the same operations for a grass texture as they would for a brick wall, so why should the algorithm? Now, because it's such a core part of our workflow, and frankly, because it's the way every single art tool is going to work in 10 years, I'd like to take a moment and tell you a little bit about how machine learning works. Now, don't worry, I'm going to get a little bit into the weeds here, but I want to emphasize that this stuff isn't that scary, and you don't need a PhD in AI to use these tools or even to appreciate how they work. I just want to offer you a little behind-the-scenes understanding so you feel more comfortable. The main idea behind machine learning is that algorithms are able to improve automatically through experience rather than their direct programming. Thus, ML algorithms are given data and they customize what happens based on that data. Machine learning at its core is statistical in nature. This is important because it lets us leverage a whole body of mathematics and algorithms to modify and interpret probability density functions. Let me show you an example. This is a visualization tool I threw together real quick to help illustrate what the machine learning process is doing under the hood. Going back to the seam removal example I just showed you, here's what the problem looks like to a computer. First, the computer needs to reframe the problem into something it can relate to mathematically. That's why the image on the left has been turned into a point cloud on the right. The green points come from the green pixels in the center, and the red points come from the red pixels along the seams. So what is this point cloud exactly? It's really just a summary of what the image looks like around each pixel's location. So it's kind of like taking little crops of the image around each pixel. If you think about a 10 by 10 pixel sized crop, that's 100 pixels. Then when you multiply that by the 3 color channels, you're looking at 300 unique values that you need to store for each crop. Or if you think about it the other way around, that's a single point in a 300-dimensional space. If we were to gather these crops for each pixel in the image, then we can treat the image as a point cloud in our 300-dimensional space, the same way we have a point cloud in a 3-dimensional space here on the right. Now, there's a couple problems with using crops directly. The first big problem is that they use a lot of memory. At 10 by 10, it's still kind of manageable for our algorithms, but what if we were to increase the size to 100 by 100 pixels? That would be 30,000 dimensions, and it'll probably make our computer explode. The other problem is that each pixel in the original image translates to 1 point in our now 30,000 dimensional space. So that space is going to be mostly empty. 30,000 dimensions is just way more capacity than we need, and it actually makes it harder for the computer to understand how each point relates to the cloud as a whole. So in this example, you're seeing the space condensed to 3 dimensions so we can make a nice visualization. But it's also a good idea to distill our information to a space that's both smaller and more meaningful to the problem. This is the first part of the process where we start to use machine learning, and there are a number of ways to do this. Now, again, don't worry, you don't need to understand any of this to use the tool. The only reason why I'm talking about all this stuff is just to dispel some of the mystery around machine learning so it's a little less of a black box. So for some problems, you can go for a supervised ML algorithm that does classification. This essentially means you're teaching a neural network how to recognize what's in the image. By training it to do that, you're actually computing a transformation function that turns that 30,000 dimensional raw pixel data space into a perceptually meaningful lower dimensional space where different axes relate to common image features like shapes and gradients and that sort of thing. Alternatively, you could also use an unsupervised machine learning method, which would reduce the dataset without having to be pre-trained. This is also known as dimensionality reduction, and there are a bunch of different algorithms to do this. This comes in handy when you have data that doesn't necessarily relate directly to human perception. So basically, that's what we're showing you in this visualization. The image features around each pixel in the image on the left has been transformed into a point cloud on the right. This is a nice way to frame our problem for the computer because now we can observe something very interesting. While some of the red points overlap with the green, we also see blobs of red points sticking out from the rest of the cloud. Statistically, these points are called outliers, and they come from our ugly seam lines. The reason why they show up in our point cloud further away from the center is because they visually look different from the rest of our image. And this is basically what we want to fix in seam removal. So now we can rephrase our seam removal problem in a way that the computer understands. We want to change the pixels in the red portion of our image so the corresponding red points in our cloud match our green points in the cloud a bit better. Now, this is, of course, easier said than done, because keep in mind, each pixel in the image actually contributes to a bunch of the crops since they all overlap with each other. This means that if you update a single pixel, it'll move a bunch of the points in our cloud all at once. This is a hard problem to solve, but again, that's where machine learning comes to the rescue. The end result, after all these algorithms do their job, is that the red points are turned into these blue points. You can see in the visualization that the blue cloud changed its shape a bit and condensed, so the outliers shouldn't be too extreme anymore. Now, if we bring back the green points in the center, you can see that the new blue points actually do fit the distribution pretty well. Now that we've seen the difference between how procedural and machine learning works, I want to point out that the two aren't enemies and you don't have to choose between one or the other. In fact, the two are actually really compatible and their combination actually gets you more than the sum of their individual parts. While procedural doesn't get you the kind of quick automation wins that you get with ML, and while it's fundamentally not good at working with example data, it does get you precise rule-based control over your generative art project. This is very important for making an ML approach practical in a real-world production, and so it's guided our design choices all throughout the development of ArtEngine. Our head of product, Eli, is going to walk you through some projects to help illustrate how all these concepts work together in practice.
Okay, so we have a few use cases to go through to show you some of the power of ArtEngine. Before recording this, we wanted to capture some real-world textures to use, so we grabbed our cameras and did a little bit of trespassing. With that done, here we are in ArtEngine, and you could see the image of a wood fence which has been scanned or photographed just by an iPhone 11. This was captured using a photogrammetry process, which was done very quickly. The idea being that we just really wanted this to be pretty easy just to get some data in here. And so now what we're going to do is we're going to convert this image of a wooden fence into some floorboards. And you're going to kind of see this whole process start to finish. So we started with an 8K image. And the first thing to do really is to crop it down a bit to the edge of the desired details. We can fix any skewing while we're at this. Also, 8K is a bit of overkill for this example, so we're going to reduce that down to about 4K. Now, starting our cleanup process, we can remove this gradient and really just sort of switch back and forth and see how that looks to kind of even things out. We can also perform some de-lighting using something called our albedo generation node. You can actually blend these two together to have more control over the de-light process. Really, sort of fluctuate it, just get it where you like it. And that's an important thing to highlight about the node graph. We have full control over the process. The order of things, the order in which we do things, how they kind of work together, that's all really something we can choose, we can pick. Next, we can mask to remove all of the spaces in between the boards. Since this is going to be a floor, you're not going to need those spaces like a fence would. I mean, unless it's a really crummy floor, but that's entirely up to you. Now the color to mask node is going to allow us to easily remove some of these imperfections like these knots that wouldn't exist in a floor. Now, just masking that data out is going to leave some gaps in our images. We need to put something in there. And so we're going to use the content-aware fill. And what that's going to do is that's going to kind of cover up those imperfections and fill that area with part of this wood grain that makes sense and blends very seamlessly. Now the next thing we're going to look at is a bit of a procedural workflow. It's going to allow us to remove seams so we can tile this floor, more than once. Obviously that's important for a floor. Now we have nodes to remove seams very easily, and we're going to look at that in this next example. But I also wanted to show you how you can clean up this very sort of tricky organic seam as well. The reality is there's a lot of ways to achieve this stuff, and we have a lot of options and nodes that are going to get the results that we want. Now with that done, we have this seamless texture, and we can use this mask paint with lines node to assist us in the generation of a normal map. We can blend the floorboard lines with other normal map data generated directly from the diffuse map. This leaves us with a very realistic looking normal map. Again, the important element here really is that we were able to take a diffuse map, a photo really, from a photogrammetry workflow and generate a cleaned up albedo and normal map from it. From here, we can use color match nodes to create variations and actually a lot of just weird, interesting, cool possibilities. And again, all from an original data set that is much lighter and really captured a lot faster than what's usually required. Before we sort of wrap up this example, and while we're looking at a few others here, another thing to highlight really is the level of parametric control available that really enables us to go wild. We can change just all sorts of stuff with this. And we could continue iterating on this, or, if we're really happy, we can move on to the next item on our list. In the next example, we're going to look at some concrete. This time, we have a diffuse and normal map, and we can see that it needs a little cleanup, starting with some gradient removal. Next, I want to show you something kind of cool. So we can actually use the mask tool and then invert it to basically select a sample of our image. In this case, we can select the sharpest parts of the image. Then, using the mutation nodes, we can actually apply sharpness from the selected areas to the entire texture. So if I zoomed in, you can see the area I took the original samples from. And you can see how that's been applied all over this texture. Now, not only is this applied in an intelligent way, it also has removed the seams from our texture. Once we're done with this sort of general processing, grabbing the parts that we want, we can further refine to get us, exactly to the end solution that we're looking for. So even though we already have a normal map, we can go so far as to generate a second normal map from it, to create some variation and make some very interesting changes. All of these options, of course, are controllable through these node parameters. Next, I think we'd like to generate a height and roughness map. Now, we could do that, in some old boring way, but I prefer to use good old-fashioned trickery. So to do this, we can actually generate noise here by applying a color mask to the normal map to take out some of the highlights. Once we've done that, we can actually blend that with the grayscale of the albedo, And the result is this new sort of roughness map that highlights the high points of our edges and gives us this really cool visual effect. Then we can generate a height map directly from our normals. And now again, we can see an example where we bring in some data from the field, gathered very quickly, and just sort of figure out how much we can clean, modify, refine it. And again, these were captured, with a cell phone camera, which, for anyone who's been doing this a while, is absolutely insane. Okay, so on to our last examples here, and really want to focus on how ArtEngine deals with patterns. So you can see here that we've brought in some maps from a sort of weave, wicker, fabric thing. This is something you might find in some IKEA furniture or, I don't know, other fine furniture outlets. I don't know. Anyway, so we're using photometric stereo, basically bringing in 8 images, and then we want to prepare it. So we're gonna crop it. We're gonna smooth out, the gradients on it, the standard stuff, we've looked at in the previous 2 examples. Now, this is looking better, but there are obviously some seams with a pattern like this. So we can use these nodes to actually guide the AI to recognize the pattern in the material. So by giving it just a little bit of information, it's able to flatten this out, and that in turn allows us to make it seamless. So once the AI recognizes the pattern, it can repeat that infinitely. From here, we can add things like a height map, and in this case, we're going to smooth that height map out a little bit, soften it up a little bit. And in the end, we have a very nice render of this wicker basket material stuff. We take this stuff, we bring it in, and we make it production ready, kind of easy. Better living through, AI assisted artistry. I'm gonna quote that. Now, we have some wool, which is a cool example because it's something that would take us, a long time to make procedurally, right? There are lots of little hairs and strands and threads that make up this wool. It would take us a really long time to generate this. So again, we can crop this down to the parts that we want. And again, that obviously is going to leave us with some seams. As we saw before, we can flatten this image. This time we're going to flatten it with a pattern unwarped node. And then, just like before, we can guide the AI, say, hey AI, here's what we want to do. This is the pattern, help you recognize it. And it's going to do the rest of this work for us. Now, I am not really an expert on wool, but I think that's some pretty high quality looking wool that we have right here. From here, we can apply a few modifications, change our sizes, again, create a height map, and again, remove any gradients that happen to exist. And in the end, we have some really great looking wool. We brought it in, a little bit of work, and we're good to go. By providing some information and context to the AI in ArtEngine, it can assist us in generating a lot of elements that would take us a very long time to capture or generate by hand, right? So we work with the system and it speeds up our process, allows us really to create some really cool stuff.
So now that you know who we are and what we do, let's jump back into the big news. Artomatix has joined Unity, and this is a big deal for our users and the industry as a whole. For you, the user, this means that ArtEngine and all the stuff we're showing you in this talk is about to get a whole lot better. It means you're going to see some new art creation tools coming out of Unity, and they're going to help you build your game faster from start to finish. It also means that you're going to have access to machine learning tools for the first time ever. The other big takeaway is that you're going to start seeing some of this technology show up directly in the game engine itself. Now, just to be clear, this doesn't mean that the game engine is going to replace ArtEngine, more that there are going to be some new powerful features under the hood. In addition, we're working on ways to bridge everything together, so when you work on a material in ArtEngine, you see it automatically update directly within Unity. Now, I would love to tell you about some of the new standalone tools we're working on, but it's still a little early to publicly announce them just yet. Instead, I'd like to switch gears slightly and talk about the behind-the-scenes discussions that led to Artomatix joining Unity. So, as many of you know, Unity's been placing more and more emphasis on artist tools and content creation over the last few years, with additions to the engine like VFX Graph, Pro Builder, and other really awesome stuff. While this has been going really well, Unity wanted to move faster and felt that it made sense to create an entirely new division to focus exclusively on standalone art creation tools and technology. Unity reached out to us about this time last year to pitch a vision they had for turning Artomatix into this new division. At the time, we just released the commercial beta for ArtEngine, and we were seeing some really nice adoption in the AAA, but we were also only 20 people working out of a small office, and we felt we didn't have the resources to go after our big vision. So it was really perfect timing and a perfect fit. Having now joined Unity, we're in the process of moving into a new building where we have the room and the headcount to grow to over 100 people by the end of next year. This will be 5 times the size we were a few months ago, so we'll be able to move faster and build new products. Unity's entrusted this very exciting mission to us because we share the same vision and they believe in our expertise. This is a belief that's been built over years. While you may have just recently heard of Artomatix or haven't heard of us at all, we've been quietly working away in the background building this technology for a really long time. Lots of research and development had to go into making ArtEngine something ready for industry, and Unity's been helping us along the way to do this. Here's a screenshot from a project we worked on together almost 4 years ago. So now that this technology is ready for the industry, and the industry is ready for this technology, we felt it was the right time to formally join Unity and step into the light. Which brings us back to ArtEngine. Let's go a little deeper into what we have to offer you today. As I've mentioned, our first product is a material authoring tool based on combined machine learning and procedural workflow. And I'd like to talk a little bit about the design philosophy that went into that. I've already mentioned that the example-based workflow is a 3-step process. First, you gather example data. Next, you provide human intent. And finally, you automate. I'd like to go a little deeper and talk about each of those 3 steps. On the data side of the workflow, you can really just keep doing what you're already doing. You can gather data from libraries, scan or paint it yourself, whatever. Our workflow is really more focused on adding human intent and automation. I've mentioned that we combine machine learning with procedural functionality, and that procedural component is really where the human control comes into play. It lets you script the ML features together with more complex operations and round them out with pure procedural functions like noise and shape generators. We also have your standard image processing features like hyperblend and all that kind of good stuff you're used to. The other way artists can provide intent is through painting masks that help guide the ML operations. So you can think of this as it lets you direct automation in a painting by numbers kind of way. The area that really makes ArtEngine stand out is the AI functionality. And this can be broken up into 3 main categories: enhance, expand, and transmute. The reason why you'd want to enhance is if you have old or low quality data that you need to bring up to some modern standards. UpRes is a great example of this. Lots of older artistic content still looks great, but needs to be remastered. We offer 2 modes for this, Tune mode and Realistic mode. Sometimes when you grab images off the internet to use as raw materials, they can suffer from some pretty bad JPEG artifacting. We've trained a neural network to clean those right up and bring back the original details. So enhance is for any asset that needs these types of fix-up operations. Expand, on the other hand, is for assets that already look great, but you just don't have enough of them. Expand starts from a small example and makes more of it. It brings the richness and variety of the real world into the digital realm. There's plenty of examples of expand features in this presentation already, so I don't want to bombard you guys with more. Just wanted to highlight one that I think really stands out above the rest. It was created by Pete McNally, a tech artist at Habit. So Pete went to a cliff face with his photogrammetry gear and scanned this beautiful rock wall. And then he went into ArtEngine and mutated it out to cover a much bigger space. He then went into a 3D modeling program and made this kind of warpy cylinder and applied his material on it and wrote a blog post called The PBR Cave in under 60 minutes. I think this is a really cool example because it really highlights how you can get from 0 to the 80% mark super fast using example-based workflow. In any case, that's enough about expand, because we've already covered that quite a lot. Let's move on to transmute. So transmute changes some basic nature or characteristic of an asset, tailoring it to some specific purpose it wasn't previously really suitable for. These features come in handy when you have high quality assets and you have enough of whatever it is you needed, but it's just not fit for purpose in some way. Like if your game were a puzzle, these features help make the pieces fit together. A great example is color transfer. This lets you update the color and material properties so that one material imitates another. You saw an example of this in the wood fence demo where multiple images were used to change the look and feel of the final result. I want to show you another feature that lets you control your colors, but in a more precise way. I also want to highlight that ArtEngine isn't just a tool for modifying scans or even just for editing materials. The plan is for ArtEngine to become a robust artistic tool for everyone. As such, I wanted to show you an example of how you could use ArtEngine to help make a 2D game. First, I grabbed the sprite sheet off of the Unity Asset Store. I really like this little dragon warrior guy and wanted to play around with him a bit. Since I just took a screenshot of the sprite sheet, it's full of JPEG artifacts, so the first thing I should do is run it through an enhance node to clean up the image. Cool, so now that it's sharp and less noisy, we can add a color transfer node, which automatically generates a color palette for the image. By default, it chooses the top 5 most representative colors for the palette, but you can set this to any number you want. You can also override the palette colors that ArtEngine chooses with your own. Anyway, the default color palette looks fine, so let's start modifying. To start, let's change the dragon's skin. Instead of orange, I'd prefer a dark green, so I just select the orange palette in my properties panel and select the color wheel. I move that over to green and select, and cool. Now that the skin's green, I think I'd like the wings to be dark red, so I'll just repeat the same process. And then lastly, that brown hair would look better black. Cool, there we go, all done. So let's zoom out and look at our whole sprite sheet. Because this method updates the color space itself, all the little dragons were modified together. If they were broken out into individual images, that would be okay too, because we could still batch process them with our new batching node. So now let's switch back to our original image so we can see the difference. This is something we could always do before in image editing software, but now we can do it a lot faster, in just a few clicks. It's a great feature for taking assets from a library and tailoring them to your specific game, 2D or some kind of 3D thing from the asset store. This is also an important feature to highlight because it's not actually using any machine learning. It's still modifying point clouds like we saw earlier, but it doesn't require any learning to do so. See, color space is only 3 dimensions, so there's not really a need to reduce that. And by modifying the palette colors directly, the user is telling ArtEngine exactly how they want the point cloud to be transformed. Now, that's not to say this feature isn't powerful or complicated or wasn't difficult to implement, quite the opposite. I just want to highlight that while we use AI for a lot of the stuff we do, there's no rule that says we always have to use AI for everything we do. Our only guiding principle is to be pragmatic and do what's best for the user. To that end, I'd like to highlight our unwarper node. We already showed this off in the cloth demo, but I wanted to highlight it again since it came directly from a problem we observed with people trying to scan cloth and other textiles. It's a hard problem to solve with general image editing software, and one AI makes a lot of sense for since it's essentially a computer vision problem. I also wanted to highlight pattern unwarp node to highlight the other main use case for ArtEngine. In addition to material authoring, ArtEngine has a lot to offer anyone who wants to scan. To this end, we've got some nice scanning features built into ArtEngine already, and we're working on more. First, there's image to material generation, a must-have for any material authoring tool. And of course, we're always improving this with AI. To that end, we've got an albedo generation and hard shadow removal nodes, and it can delight real-world photographs. And we've added support for multi-light source scan processing. So we're working on some new features, and we should have more to share at the next Unite. Which brings us to our 2020 roadmap. I'd like to share some of the high-level plans for the rest of the year. One big push is for smart material support. Right now, ArtEngine loads bitmaps and saves bitmaps. In between, you build a graph, and that does some processing from input to output, but that graph only lives in your ArtEngine project. We're implementing a compound node system, so you can take a large and complex graphs and bake them down into a single nodes, and then use them within other ArtEngine graphs or export them as smart materials to be used in other tools. This is going to fundamentally change the way you'll use ArtEngine, both on its own as well in combination with other tools we're building. Let me give an example of a smart material. We grabbed these two marble textures from a library. They're super nice scans, but in their raw form, there's only so much you can do with them directly. Our goal is to quickly turn this data into an infinite marble floor smart material. First, we need to do a little extra work to the scan on the right. It was taken from a real-world marble floor pattern, and the tile is actually two distinct marbles, and we only want the texture on the outside of the borders. So if we highlight this area with a mask, we can use our mutation node to create a new unique 4K tileable material from just those bits. Just as a quick throwback to that point cloud visualization I showed you earlier. This brings us to our other big development for the year, combining the example-based workflow with painting. We've already developed a form of our mutation that can be guided by a mesh, so the new synthesized material will conform to the UV space and you won't see any stretching or seams on the model. This will let you paint your smart material directly on the mesh itself. Here's an example of an off-the-shelf asset being updated quickly. It makes texturing your models super quick and fun. Anyway, this is what we'll be up to for the next while, and we're looking forward to showing you our progress at the next Unite. To wrap things up, we'd love to get your questions on the forum. And if you'd like to get started with ArtEngine, please reach out. And lastly, thank you for tuning in.